For centuries, people pondered the mystery of motion. Ancient philosophers like Aristotle believed that objects had a natural tendency to be at rest. To keep something moving, you seemingly needed to apply a continuous force. Push a cart, and it moves. Stop pushing and it comes to a halt. This seemed intuitively obvious. However, this Aristotelian view had its problems. For example, why does an arrow continue flying after it leaves the bowstring? There's no longer any visible force pushing it forward. These inconsistencies puzzled thinkers for generations. The world awaited a new explanation, a deeper understanding of how objects behave when forces act upon them, and when they don't. The stage was set for a revolution in scientific thought. Enter Isaac Newton, a brilliant English physicist and mathematician. In 1687, he published his groundbreaking work, Mathematical Principles of Natural Philosophy. This book laid the foundations of classical mechanics and our modern understanding of motion. Central to Newton's work were his three laws of motion. The first law, often called the law of inertia, stated simply, an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. Imagine a hockey puck sitting on a smooth, icy surface. Give it a gentle push, and it glides effortlessly across the ice, traveling a significant distance before slowing down. Now, imagine pushing the same puck with the same force across a rough wooden floor. This time, the puck quickly comes to a stop. What's the difference? The smoother the surface, the less friction there is. Friction is a force that opposes motion. On ice, there's very little friction, so the puck continues moving with nearly constant velocity. On wood, however, there's much more friction, causing the puck to decelerate rapidly. This tendency of an object to resist changes in its state of motion is called inertia. The heavier an object, the greater its inertia. Think about pushing a shopping cart. An empty cart is easy to accelerate and decelerate, but a cart loaded with groceries has much more inertia, making it harder to get moving and harder to stop once it's in motion. Inertia is a fundamental property of matter, just like mass or volume. It's the reason why you feel a force pushing you back into your seat when a car accelerates and why you keep moving forward when a car brakes abruptly. Section 5 Friction, the motion thief. In an ideal world with no friction, an object set in motion would continue moving forever at the same speed and in the same direction. However, our world is full of friction. Air resistance, rolling resistance, and surface friction are just a few examples. These frictional forces act like invisible brakes, gradually slowing down moving objects. That's why the hockey puck eventually comes to a stop, even on a smooth ice rink. The friction between the puck and the ice, though small, is not zero. Section 6. Inertial frames. The right perspective. To understand Newton's first law fully, we need to consider inertial reference frames. An inertial frame of reference is one that's not accelerating. Imagine sitting on a train moving at a constant speed in a straight line. If you close your eyes and ignore any vibrations, you wouldn't be able to tell if you were moving or standing still. That's because you're in an inertial frame. Now imagine the train suddenly accelerates. You'd feel a force pushing you back into your seat. This force is a consequence of the train's acceleration, not because of any direct interaction with another object. You're now in a non-inertial frame, and Newton's first law doesn't hold in its simplest form. Section 7. Beyond the basics. Newton's first law in action. Newton's first law isn't just an abstract concept confined to textbooks. It's a fundamental principle that underpins our understanding of the universe. It explains why planets move in elliptical orbits around the sun, why satellites stay in orbit, and why cars need brakes to stop. Engineers use Newton's first law to design safer cars with seatbelts and airbags. These safety features are designed to counteract your body's inertia, preventing you from continuing to move forward during a sudden stop. Section 8. Understanding our universe, from Earth to space. Newton's first law even helps us understand the large-scale structure of the universe. Galaxies are vast collections of stars, gas, and dust, held together by gravity. Their motion and evolution are governed by the same laws of physics that we observe here on Earth. From the smallest particles to the largest celestial objects, Newton's first law provides a powerful framework for understanding the universe we live in. Section 9. Conclusion. The enduring legacy of Newton's first law. Newton's first law of motion might seem simple at first glance, but its implications are profound. It challenged centuries of established thought and paved the way for modern physics. By understanding the concepts of inertia, friction, and inertial reference frames, we gain a deeper appreciation for the world around us. Newton's first law is a testament to the power of scientific inquiry and the elegance of the universe's underlying laws. It reminds us that even seemingly simple observations can lead to profound insights into the nature of reality.